Welcome back, boys and girls. Daniel here for Rock the JVM, and in this video I'm going to talk Apache Spark, and in particular I'm going to talk about broadcast joins as a very nice performance optimization technique. Now, this video will assume that you know some of the Spark fundamentals, including how to work with data frames and how joining works, at least at the API level. As always, I'll recommend that you code with me in this video, either in a dedicated Scala application or in a Spark shell, and whenever you need to refresh your memory, just refer back to this video or to its written version at the blog with the link in the description attached to this video. Now, for this video, I'm going to work with Apache Spark version 3.0.1. So if we go back to the code, in my IntelliJ IDEA, I've already added the Spark library definitions in build.sbt. So if you go to build.sbt, I have here some lines here, org Apache Spark, %% Spark core, %, and the Spark version here that I've defined at the very top of the file is 3.0.1. So we're working with Spark version 3, and what you need to do is add these two lines in your build.sbt file. You can also find these two lines in the blog version of this video. Alternatively, you can go to spark.apache.org and download a dedicated installation of Apache Spark. So click this bright download tab over here, and you will navigate to this page, which gives you a precompiled version of Apache Spark with all the right executables that you can execute for your operating system. And the executable that I recommend you run for this video is Spark Shell, which you can find in the bin folder after you download this zip file. And into the Spark Shell, you can type in the exact same code that I type here in my dedicated Scala application. All right, so these are the two alternatives that I recommend you follow if you want to test the code that I'm about to write. Now, if you chose the dedicated Scala application version, you will have to initiate a Spark session, which Spark Shell already has. So I'm going to define a val called Spark, which is Spark session.builder, and I'm going to give this session an application name. I'm going to name this broadcast joins, and I'm going to set master to local. So this is Spark master, and then I'm going to call get or create to obtain the Spark session. So this line you don't have to write in the Spark shell because the Spark shell already has a Spark session already set up for you. Cool, so let's get to the meat of it. So here's the scenario. Let's say we have a huge data set. So I'm going to define a huge data set. I'm going to call it table. And in practice, this can have billions or even tens, hundreds of billions of records. And just to make this demo runnable on a local machine, I'm going to use a decent number like 100 million or 10 million or something like that. And I'm going to write spark.range, and I'm going to add 1, and then I'm going to add 100 million. So this is a data set of long with 100 million longs, okay? This is the so-called huge data set. At the same time, we also have a small data set, which can easily fit in memory. And for some reason, you need to join these two data sets. So I'm going to define, let's call this rows as a Scala list, and I'm going to use spark.sparkContext, which is the root endpoint of the low-level Spark API. So I'm going to create an RDD out of a Scala list, and I'm going to call parallelize, and I'm going to pass in a regular Scala collection, and I'm going to pass a list of row objects. So I'm going to define row, and I'm going to import row from org Apache Spark SQL. So data frames, as you are probably aware, are data sets of this type. And I'm going to create a list of rows, then I'm going to parallelize it. I'm going to turn that into an RDD of rows, and then I'm going to create a data frame out of it. So I'm going to define a row with two values. I'm going to have one with gold, and then row with 2 silver, and then row with 3 and bronze. And by now, I think you have a good intuition of where I'm getting at. We have 100 million integers or 100 million longs, which I'm going to join with this very small data frame to obtain the gold, silver, and bronze medal lists from a list of a very, very large number of so-called participants. But I digress, so let's create a data frame here. So I'm going to define a schema. So I'm going to say rows schema as struct type. And this struct type will have an array of 2 fields, so array. And this schema will describe these rows. And in our case, we only have 2 columns here, an integer and a string. So I'm going to define a struct field that I'm going to import with the name ID and the type integer type. And you need to import integer type from Apache Spark SQL types. And then a very similar thing with, let's say, medal with string type, which I also need to import from Apache Spark SQL types. Now, I need to turn this RDD of row, so this is an RDD of row, and I need to turn that into a data frame. So I'm going to define this as a lookup table of type data frame. Okay, and I'm going to use spark.createDataFrame, and I'm going to pass in the RDD that I've created above. So I'm going to pass in rows. All right, and after I pass in rows, I also need to pass in the schema. So I'm going to say rows schema, and this is how you turn an RDD into a data frame. This RDD must be of type row, which is why I've created these 3 rows, and then I've turned that into a data frame. And as you are probably well aware, the data frame API allows us to write SQL-like functions. Now, turning back to our scenario. So we have a huge data set with 100 million rows and a very, very small data set, which contains just 3 rows over here. And for some reason, we want to join them. And in our very simple use case, we have 100 million participants in a competition, and we have recorded their positions in the contest. And we want to see which one of them deserves the gold, silver, and bronze medals. And for that, we need to join these 2 data frames. So if we wanted to say, let's call this joined as table.join lookup table under the column ID, which is the column that is common to both tables. So the first lookup table has the column ID because I've specified that in the struct type, and also the huge table also has the column ID because spark.range creates a data set of long, which can also be interpreted as a data frame with a column ID. Okay, so column ID is the common matching column that we are going to use for joining. And if we wanted to say joined.show, just to see which number got the gold, silver, or bronze medals, this is how we would show this table into the console. And because I've created a Scala application, I also needed to add a main method inside this object that I've created so that we can show this result into our console. And just so that the Spark application doesn't finish after we call show, I'm going to do a thread sleep. And I'm going to pass in a very large number so that we can also inspect the Spark UI to see how long this kind of join will actually take. Okay, so this technique should be pretty simple, and the time for this join should also be pretty small because this rows RDD and therefore the lookup table is very, very tiny. And so we have 100 million elements joining with just 3 elements. And so this job over here where we clicked join.show shouldn't take too long. And let's see how long it actually takes. So I'm going to run this application, taking a few seconds to compile our code. And I have lots of code from all the other videos here on the Rock the JVM channel. So this will take a little bit of time. And also Spark will also take its couple of seconds to start. Cool, so we have our logs over here, and notice that Spark has actually started working. Now, in the meantime, I'm going to open a browser tab, and I'm going to navigate to localhost 4040, where I'm going to have the Spark UI for this particular job. And notice that the job already has taken 13 seconds, and it hasn't stopped yet. So Spark is still working. So this job is taking north of 20 seconds. So now that I've refreshed the page, notice that Spark has split this initial job into multiple small jobs, and the first one took 16 seconds, and then 2 seconds, 7 seconds, and 5 seconds. So in total, roughly 30 seconds to join 100 million elements with a data set of just 3 rows. And if you can hear the hissing in the background, that's my laptop taking off. However, the result is correct at the very end. So notice that we have ID 1, 2, 3, and then the metal, gold, silver, and bronze attributed correctly. So the join worked correctly, but why on earth did it take 30 seconds to join just 3 elements into this operation? Now, if you ever wanted to debug performance with your Spark jobs, you will need to learn how to read query plans. And we have a dedicated video on the channel to teach you how to read query plans in Apache Spark. And to debug why this particular join is taking so long, I'm going to say joined.explain. And join.explain will print a very cryptic piece of text, but it's also very dense in information, and it shows us the kind of deconstruction that Spark will perform before the job actually runs. So join.explain will simply show us all the steps that Spark will perform before actually starting the computation. So I've restarted the application, and this time it'll take just a couple of seconds. And notice that this text will describe the join that we're about to perform. So we can read this query plan either from top to bottom or from bottom to top. And in this case, I'm going to read it from top to bottom, and we can read it like this. The joined data frame is this final step that is a project step with ID and metal. These are the columns that Spark will keep in the final data frame. Now, this final project step depends on the join, which is the last operation that Spark will perform on the 2 data frames. The actual join mechanics that Spark will apply is a sort merge join. A sort merge join will basically sort the keys. Because the keys are numerical, Spark will attempt to sort these 2 data frames so that the keys are in order and so that the matching keys can be found on different executors, because as you know, Spark will run independent computations in parallel. All right. Now, this sort merge join will also depend on 2 wildly separate branches. This one, and then the branch below it. Notice that these text-like column over here will separate these 2 branches. The first branch will need to sort the big data frame. Okay, so we need to sort ID #0. So this is the identifier on the first data frame. And before we can sort, we need to exchange hash partitioning. This is very important. Whenever you see exchange, then that means Spark will redistribute the data according to this particular scheme. So Spark will redistribute the data in between the executors in your Spark cluster. And data exchanges are also called shuffles, and they are very, very, very expensive. Because data exchange takes time, exchanges like this will be the bottleneck in your Spark performance. And if you remember, we have 100 million elements to redistribute in my local computer. So imagine if you had 100 billion elements redistributed in your cluster with network, so network transfer, that would have taken hours, if not days, in your data pipelines. So this exchange is particularly expensive. And the first step over here is just the range construction, which is pretty cheap. Now, the branch below it only needs to deal with the very small table, which is pretty negligible. Redistributing a very small table takes very little time because this table can fit in memory on a single computer, let alone in many computers. Okay, so this particular exchange over here on 100 million elements is the bottleneck in the performance of this particular join, which explains the wildly obnoxious duration of 30 seconds to join just 3 elements with 100 million elements. Now let's get back to the code and let me show you a way to mitigate this particular join performance in the case where you need to join a very large dataset with a very small dataset. Enter broadcast joins. So fundamentally, Spark needs to somehow guarantee the correctness of a join. This is why this exchange is required. Normally, Spark will redistribute records on both data frames, which is what's happening here, by hashing the joined column, so that the same hash implies matching keys, which implies matching rows. Now, there is another way to guarantee the correctness of a join in this particular situation, where you have a large dataset joining with a small dataset, by simply duplicating the small dataset throughout your entire cluster. So in this way, each executor will have all the information that is required to perform the join at its location without needing to redistribute the big dataset. This is called a broadcast. And in this particular technique, I'm going to define another data frame. So I'm going to call this joined smart as table.join. So far identical, but in this case, I'm going to call the broadcast function. Now, broadcast is a function that you can import from org, Apache, Spark, SQL, functions, broadcast. So you can import broadcast independently, or you can import all the functions via an underscore. And you can call broadcast on the small table. So I'm going to broadcast lookup table. When you say something like this, then the lookup table will be redistributed, will be actually duplicated on every single executor in your Spark cluster, so that each executor does not need to exchange the big data frame, but each executor can join a partial set of the big data frame locally without needing to talk to other executors. Now, if you call join smart.explain, just to compare the query plans, you will see something that is pretty different. So I'm going to rerun the application, give Spark a couple of seconds to run, and we will see the query plans and we will compare them. So notice that we have both query plans here in the console, so we can safely compare them. Notice that the second query plan is much simpler. So the joined smart data frame that Spark will compute is a broadcast nested loop join. So notice that this join mechanics is wildly different from the sort merge join that it used to perform before. So notice that this join will only need to consider the initial big data frame, so the range 1 to 100 million, which it doesn't need to redistribute anymore, and the other branch is a broadcast exchange of the lookup table. Now, this is also an exchange, meaning that executors in your Spark cluster will exchange data, but this is a broadcast exchange in the sense that it's not a shuffle. So Spark will not redistribute the data between your executors, but rather it will duplicate the data on all the executors. And sure enough, if you actually test the performance of this join by calling joinsmart.show, so this will actually trigger a computation, and also I'm going to add the join column here. The join column is ID. Let's see how fast this join will actually be. So a couple of seconds for Spark to run, and notice that in just a couple of seconds, we have the correct result. And if we go to Spark UI here at localhost 4040, notice that the job took at most half a second. So we have job number 1 took 90 milliseconds, and this preparation took 0.6 seconds. So even less than 1 second. So in our case, we have less than 1 second, and in the first case we had 30 seconds, so we have 30x performance improvement. So the goal of this video is for you to keep this technique in mind whenever you need to join a very big dataset or data frame with a very small data frame or dataset. Just consider duplicating or broadcasting the small data frame so that you avoid a shuffle. In this case, we have a 30x performance improvement, but in practice, in real life, when you have billions of records and terabytes of data to join, the performance improvements can be quite dramatic. So there you have it, folks, a really nice performance optimization technique in Apache Spark for whenever you need to join a big data frame with a small data frame. Check out the article as well, because I also give you some indications on how Spark can automatically detect whenever a data frame needs to be broadcast, and also how to configure or disable that feature. Alright, so I hope you enjoyed this video. Click the like button for me and subscribe to the channel for more videos like this, and follow us on Twitter and LinkedIn for fresh updates on upcoming material. As always, I'm dying for feedback, so please leave your comments attached to this video. I read every single one. And check out the Rock the JVM website for tons of videos and articles like this, including full-fledged trainings on Spark performance optimization. Until next time, I'm Daniel, signing off.